Okay, sorry for the delay, everybody. Now let's go. Okay, so to understand spectroscopies, which spectroscopy is just a fancy word for some lab technique where you're using some form of radiation to do something to an atom to get information from it, okay? We need to take a sidestep just to understand how radiation works and what it is. So the term radiation can sometimes have a lot of different connotations, right? Like it can often feel like a negative thing. Scientifically speaking, radiation is just a form of energy that have wave characteristics and travels through a vacuum at the characteristic speed of light. The characteristic speed of light is a constant. We'll actually use it today in some math equations. It's on our formula sheet, so we don't have to memorize this number, but on that blank line, write 2.998 times 10 to the 8 meters per second. So that is the speed of light. So anything that travels at the speed of light is classified as light. Now, often when we think of light, we think of the light that we can see with our eyes, but there's a lot of types of radiation we can't see, but it's still classified as light. So all light travels as a wave, so some vocabulary words to be familiar with if you're not are wavelength and frequency. Okay? Wavelength measures, it's kind of small, so I don't know if you want to emphasize it on your picture here, but wavelength measures from like what's called the crest to the crest, or the trough to the trough. It's the same because it'll be symmetrical, right? Waves have a consistent wavelength. Okay, so that's what wavelength is. There's this measure called amplitude, which we won't even deal with in this class, which is the height of the wave. But the other one we will deal with is the measurement of frequency, which isn't shown on the picture because it deals with a movement idea. Now, it's different than speed. So frequency represents how many cycles, which a cycle of a wave is up and down. So how many cycles does it go through per second? Now, a common misconception I want to make sure we don't do is mixing up frequency with speed. Can anyone think of some example of how they're different, of how we can help understand it, of how can two things have different frequencies but travel at the same speed? Because all light travels at the same speed. Caleb, give us something.
If something has like a shorter wavelength, it would have a higher frequency and like the same speed as something else.
Yeah, so he's kind of visualizing, right? Like frequency would be like they're going to shrink in like this, so their wavelength won't be very long. How's my face for that? Another example or different way of explaining it? I thought I saw a hand back. Oh, same one? Yeah, Lily.
Is it kind of like with the other graphs that like it's like a string, but like you can like make it and then it like it goes the same?
Yeah, you could kind of think of like with a wave, right? Like if you pull it out, they're inversely proportionate, so the wavelength's going to get longer and this frequency will get shorter. I mean, inverse happen to it. Yeah, you can think of it like that, like a spring idea, kind of like stretching the spring versus scrunching it together. Good, have a smiley face, I like that visual. Alex, and then Bryson.
It's kind of like, to be like a highway, and you like, over the course of a second you see, or like over the course of a minute you see how many cars like pass a certain point, and if there's, like let's say 5 cars pass on one lane, but on the other lane there's 10 cars, so there's more cars, but they're all going at the same speed, and so more
Okay.
of them.
Alex is the only one who's supposed to be talking right now. Sorry, continue, Alex.
And so yeah, just more of them pass that point over that course of time.
But all the cars could be traveling at the same speed,
Yes.
right?
Yeah.
So kind of keep that in mind, like frequency sometimes feels like how fast it's going, but it's not about how fast it's going. Have a smiley face for sharing that. Bryson, do you have something else?
I think this would be correct, but like let's say you get like light from the sun.
Yeah.
It's still the same speed as the light we get from like Jupiter and like Saturn and stuff. Just it's stretched out.
Sure, because the distance now is playing a role in it. Good, that's another way to think about it. Have a smiley face for that. So here's how I sometimes think about wavelength and frequency, right, in terms of like visualizing what they are. So imagine 2 people walking down the hallway, okay? I guess we could pick people, but I don't want to make anyone feel bad, right? So imagine like a tall person, okay, walking next to a not as tall person, okay? So we could be walking down the hall at the same pace, but how's our cadence or our spacing going to be from each other? Most likely the taller person's steps would be like this, right? And if I'm going to keep up with that person, then I might be doing like this, to keep up with them. So we're traveling at the same speed, but in a sense, I have a very high frequency of steps compared to their low frequency, but they have a much longer wavelength compared to my wavelength. Does that make sense? Right?
My favorite way to see this is looking at Ryan Felt run with his massive legs. If you see him running the 400 against a regular person, you can see the regular person, like, their legs are moving fine, and then Ryan Felt is just walking.
In comparison. So Ryan's like, what, 6'8"?
He's tall.
8?
He's tall.
Maybe? Yeah, and so, but no, perfect example. Usain Bolt's another one, because he's pretty tall compared to most sprinters. And so if you see like his steps compared to the guy next to him, it's like compared to like the one he's taking because of it. So there's some good visuals. I like that one. Zach, for those that can be really good. Okay, so keep in mind there's this inverse relationship, but in the end, they all travel at the same speed. So this right here is known as the electromagnetic spectrum. It's maybe here it is. Lost my mouse again. Okay, so this tells you all the different ranges of radiation that exist in the universe as we've named them. Okay, now as they change, they cause different impacts because energy goes up, which means they're able to then penetrate through things as they get smaller and higher in energy. So radio waves, now you don't have to have these memorized, like you don't need to know the order of it. I think there's some funny, probably mnemonic device, but you don't have to have it memorized. Just be familiar with what they are. What is helpful though, which is kind of nice because they're kind of like logical, is knowing which ones are the highest in energy and which ones are the lowest. But if you kind of just think about life in general, that can help. So radio waves have the longest wavelength, and hence they're lowest in energy. This is why radio waves aren't harmful to us. If we could see them flying around outside with our eyes, like they're huge, right? Like they have a wavelength of like sometimes a meter or bigger. So imagine, like, this is my visual, I visualize like spaghetti flying outside, right? Like it's like this, right? But like they're like really long waves traveling through the air, right? As we go down, microwaves get much smaller. But in comparison, they're actually still pretty big. A cool, simple experiment you can do is if you take, excuse me, if you take a king-size candy bar and you put it in your microwave, we'll take out the plate that spins it first, so it can't spin. And you just put it in there, put it on something obviously, and then you melt it, but not too much. You actually will get two distinct melted spots on the candy bar. And it's literally showing you the wave going in and the wave coming out. So you can actually measure, like with a ruler, what is the length of your microwave. Now, our microwaves spin because we don't normally just want two heated spots in our food. We want it to be equally distributed. But this is exactly why often when you bite into things from a microwave, it could be still frozen in one spot but boiling hot in another. Is because of how those microwaves have entered and exited. You can get pockets that don't ever get heated, right? Kind of visualizing this idea of wave traveling through your food, right? So as we keep going, so they just get smaller and smaller and smaller. Okay? Once again, think of all these things as light, even though with our eyes we can't see them as light. Alex?
Just for the microwave, like what is the certain point where it does hit and heat up the food and where it doesn't? Like why doesn't it do it, I guess, variable? Like is it always a set spot on the wave?
So they have a set length that they're doing. Obviously your microwave is sending lots of them in. It's not like a single wave, right? And so that's part of it. And then the rotation is to help. And we'll get to this. The idea is as the microwave travels into the food is it causes the water molecules in there to start to spin. And the spinning is what heats it up. And so there can be obviously like that heat can spread to other things. And so then that's why it like gets distributed throughout. But that's why like a lot of things I always say, like if you can, when you take it out of the microwave, like you should stir it around to like distribute the heat. Does that kind of answer your question? And it kind of goes like dealing with like the watts of your microwave. So every microwave has a different amount of watts that it puts out, which corresponds to like the length of the wave and how many waves it's sending through.
That makes sense. I guess I'm trying to ask like why it doesn't like consistently heat and it hits one spot in the food. Like how is that? Why does it not like hit any spots before that?
So, because like literally they're like, they can be like this long, right? So like the wave comes out of the food and then goes back into the food. Does that make sense? Depending on the food and what it is.
I guess so.
Does that, I don't know if that answers your question. Not really.
Maybe I'll look more into it later.
Okay, let me know if I can answer it a different way.
Sure,
But,
sure.
so as we keep going down, once again, imagine all these things are just a flashlight idea, right? So everyone in here, has everyone had an x-ray of some kind in their life? With your teeth? Everyone's probably had a teeth x-ray, right? Right? Most people, okay, hopefully everyone has. So when you go get an x-ray, I guess if you haven't, you've seen what an x-ray looks like, right? But this is maybe a new way to think about it in this terms idea of light, okay? So if I should have just brought a flashlight today, I didn't. But if I had a flashlight, okay? Oh, duh. Genius. I don't know what my phone is, I lost it. I'm like really good at this thing. Okay, we have a flashlight on phones. Okay. Oh, it's gonna be too bright. I don't even know why I'm doing this. Okay, I'm shining a flashlight on my arm. Okay, if there was a wall on this side, what would we see on the wall? My shadow. What is the shadow showing?
Your arm.
Why? The light can't pass through it. Okay? When you go get an x-ray, they're shining a flashlight of x-rays at your arm. What picture do you see? Why? The x-ray can't go through the bones. So that's all an x-ray is an x-ray is just a shadow of what the light didn't pass through. Is it passed through everything, right? Passed through the skin and the muscles and the tissue, but it couldn't pass through the bone, and so you get the shadow image of just the bone. Does that make sense? So as radiation gets smaller in size and higher in energy, it has the ability to penetrate more and more things. So since x-rays are so small, they can pass through our skin and our muscles and our tissue, but they're not small enough to pass through our bones. And so it can't go through it. And then gamma is the smallest, which can penetrate down to the atomic level and can actually mutate DNA because it's so small. So the idea of the Hulk being created through gamma radiation does have some science behind it. I'm not saying you'd be turned into the Hulk, but the idea of it is there. So, okay. Do we have like a decent kind of visual as you're visualizing waves and like how they work? Bryson?
Is our lab gonna be someone getting blasted by gamma rays?
Draw straws. No, but it is kind of cool. So like they use gamma radiation. So it's like obviously gamma radiation can be bad if exposed to it in uncontrolled ways because it can cause cancer because it's changing your DNA, right? Changing the cells. But they also use it now to treat cancer because they can control it, and they have these things called gamma knives, right, where they actually use it to get rid of all of it. At SUU, we actually had this cool, they actually did an experiment where they took some strawberries and sent gamma radiation through them, because radiation just travels, it doesn't stop, so it's not like it's still radioactive like after. And it killed all the bacteria in them, and so they stayed fresh for like way longer than like. So it was like a really good way of like preserving food, actually.
Yeah, want your fruit to stay fresh.
But if you just have some gamma on hand. But yeah, Allie.
I was just kind of curious, are you guys like in a terminal place like in an uncontrolled environment? Have they found like the patterns in a way like
I'm not entirely sure. As the most that I know they kind of know like the certain level. So people who work in areas with high levels of gamma wear like a thing that detects how much radiation they're getting, because there's like a certain level that they've kind of identified, like if you get past this, like that's not going to be good for you. But in terms of like how it influences you, I don't know if there's any like rhyme or reason to it. Yeah, it's even somewhat similar to like X-rays, because even X-rays, even though they can be harmful to you if you're overexposed to them. That's why like the nurse, after they like get you set up, where do they go? Right, they leave while the X-ray's running. And what do they put on your body? Yeah, a big heavy lead blanket, because they don't want to send X-rays through things that don't need to be X-rayed. It's also why it's pretty rare now, as far as I know, to ever get an X-ray of your head done. They won't do X-rays. Instead, they'll do CAT scans or MRIs because they work differently. And I've even heard that they'll limit how many x-rays you get in a year. Like if for some reason you've had a lot of injuries, like they're not gonna just like keep x-raying you because they don't want to overexpose you to that radiation either. So yeah, but I'm not sure if they have any data in terms of like, it always affects this area or that area. Yeah, that's a good question. Okay, so with this idea, let's dive into each one separately. So this is the one Caleb reminded us of. So this is now getting into the chemistry side of it. Okay, if I use this type of energy and I shine it at an atom, what does it do to the atom, and then what data can we get from this? How can this help us? Okay, so this type of spectroscopy is our photoelectron spectroscopy, our PES spectrums. This look familiar now? Remember these graphs from Unit 1? If we don't, we'll remind ourselves in April when we review everything. So hopefully it kind of looks familiar. Okay. This one, once again, just like Caleb said, I'm going to draw a little picture here if you want to add it to help remind you. So the idea is you have your atom, right? The electrons are orbiting around it. I send the X-ray in. X-rays have so much energy, so these are our high ones. Right? They have so much energy that when that little electron absorbs it, it bing, flies completely off the atom, and then this ends all of them end up getting shredded off. So what this does to the atom is it actually ejects the electrons or removes the electrons from the atom. By doing this, what we are able to do is we can then identify an unknown element. Right? So we can then use these graphs and we can say, hey, I know what this is because of the pattern of what the electrons did. So this is why scientists use this method, or at least one reason why they do PES spectrums. Okay? If you connect these two, it helps a lot because you kind of think of like, okay, what's the energy doing? How could that make the change? Okay? All right, are we good for the next one? Okay, so this one, we'll talk even more about at the end today. So this one is UV and visible light spectroscopy. They're kind of connected in the same. I should have just merged these boxes because they're going to be the same answer for both. So I'm just going to write in one, but you can draw an arrow. So now our energy is more on like the medium side of things, right? Not as high as X-ray, but higher than others. Okay, so we're going to classify these as medium energy. So now, same picture, but a little different result. So now I'm sending in UV light, which is like the light that, or the rays that burn us from the sun, right? Or even just visible light, right? So like different colored lasers. Okay, if I shine that into an atom, it's not as powerful, so it doesn't eject it, but it does cause the electrons to jump. So we talked about before this idea of an excited state. Okay, so this is what happens when you use UV light, is it transitions the electrons to an excited state. They don't get removed, but they do jump up, and in that process, we then can get information back of what the molecule is, how to identify, as well as we'll learn later today about concentration. So you can use this method to identify what a concentration is. You could be like, oh, this is a 1 molar solution by using this method. Okay? Good there? Okay, once again, so notice kind of as we go lower in energy, the effect that it's having. Okay? So our next one is infrared. This one's really cool in what they do. If you go on and study chemistry at higher levels in college and take organic chemistry, you'll learn how to interpret this fun-looking graph. This is a graph, by the way. It looks like, what are those words in caves? Stalagmites? Stalactites. There we go. That's what they look like to me. But it's actually a graph, and it's really cool how it works. In our class, you don't need to know how to interpret them. But here's what we want to know, is that if I shine an infrared light at it, they're much lower in energy and bigger in size. And so now they don't have the ability to penetrate to the electrons. The electrons are really small. So if you're going to influence an electron, the wave has to be small. So since the waves are getting bigger, they can't impact just the electrons, but what they do is they actually change the bond vibrations. Okay, so it changes the bond vibration. And when the bond vibrations change, you get these funny looking graphs out of it that represent how the bond is vibrating. So first off, what we mean by a bond vibration, because often we think vibration, you maybe think like your cell phone, right? Just like buzz, right? A vibration of a bond is a little bit different, okay? So imagine, let's pretend I'm water, okay? So imagine like my body's oxygen, and these are my hydrogens, okay? You want to see me? I'm water. Can you tell, right? Why are my arms like this? Because water's bent. Good, right? Okay. So what we mean by a bond vibration, okay, is that bonds, even though it's a bent molecule, the bonds can go like this. They can vibrate. Or they can do this. And that's a bond vibration. Or they can do this. And that's also a bond vibration. So the water molecule can vibrate in a lot of different ways. And as it vibrates, you then can get information from it. And the vibration is kind of like almost like a fingerprint in the way it behaves. Like each bond has a very particular vibrational pattern. And so when you see these funny looking graphs, there's this whole, like, you have to learn all the different patterns. But in a sense, this little section right here, this funny little shape is like a fingerprint for a type of bond. In our case, it's a C-double-O bond. And so you can actually piece together a molecule from this picture. Because each of these represents a different part of the structure. And so you can literally piece together very complicated molecules like our dopamine up here based on these funny looking graphs, which I thought it was one of my favorite parts of organic chemistry. I thought was really cool. Was throwing some random powder into the IR machine and then being able to draw a picture of what it was. So, does that make sense, the idea of what it does with vibrational bonds?
Did you say it was like, the bonds are like the fingerprints? Is it are the, I guess, so-called like fingerprints as rare as normal ones? Or is it just like,
Yeah, it's that like a tell me if this doesn't answer your question, but like a C-double-O oxygen bond always has the same vibrational pattern, no matter what it's in, and it always ends up with this picture. Just like an O, like to H bond, would always have the same vibrational pattern every single time. Does that answer your question? Any other questions on this? All right, let's go to our lowest in energy, which is microwaves. So microwave spectroscopy uses microwaves. Their graphs look like this. Another fun-looking graph which we will not learn how to interpret. But this one changes, or what it does is it affects the rotation of the molecules. As we kind of mentioned, that's how microwaves work. By doing this rotational, you can actually use it to help identify where there are hydrogens in the molecule or not. So this one is the lowest amount of energy. So it's going to have the least impact in terms of changing the molecule, and so all it changes is it rotates it. So rotation of the molecule. But how a molecule rotates can give you indications of hydrogens in the atom. So I don't know how to explain that to be honest with where we're at right now. Maybe after unit 6, I might be able to explain.
I'll ask my question right now.
Perfect. There you go. Have her explain it to you. Okay. Questions on any of our 4 types of spectroscopy? So your homework that will kind of match up to these sections is the AP Classroom 311. You'll kind of see what questions you'll see. It's really just about predicting what the radiation does to the atom and kind of matching those up. This is another one of those topics that, like, it's cool that they have us teach it to you, but it's also, like, not fair because we could literally spend so much more time really understanding it, but you're only going to have, like, 1 question out of 100 that will be about these things, so we just don't have the time. But, okay, let's take a look back at this idea of waves, and we're going to do a little bit of math with it now, okay? So this idea of how if I shine light at a surface and the electrons can be ejected was actually first discovered by Einstein, and he named it the photoelectric effect. So the photoelectric effect is just the idea of shine a light. So here's my laser. If it has enough energy, I can get an electron to fly off. If it doesn't have enough energy, then the electron won't come out. Okay, so depending, there has to be enough energy for the sample to eject the electron. Okay, so this connection of frequency and wavelength and energy are connected through two equations, which are on our formula sheet. You don't have to memorize them, just got to use them. Is everyone good if I go to the next one? Okay, so our two equations are that wavelength and frequency will always equal the speed of light. So C is the variable they chose for the speed of light.
Why?
I don't know why. Okay, so this is the speed of light. Once again, it's on our formula sheet, so we don't have to memorize it. Okay, this is the Greek symbol for wavelength. Okay, so the way I draw it is you kind of just do like a hook and a line. Some people think it's like an upside down Y. Some students call it a giraffe. Whatever helps you remember it. Okay, so this is wavelength. Oh yeah, one student last year was like, oh, it's like a little wave at the top. That's how they help you remember. Okay, so that's the symbol for wavelength. It's the Greek letter lambda, is its Greek name? You can't, lambda. And then, so lambda times nu, that's the Greek letter nu, looks like a V, and it kind of has a straight line and a curved line. This is the symbol for frequency. Once again, these are all on our formula sheets. I know they look a little weird. We just got to know how to use them. Okay? And then the other one relates it to energy. So energy is E. Okay, right? Makes sense. So energy of a photon will equal H, which is known as Planck's constant. He's the person we give credit for. Okay, it's on our formula sheet, but it has a value of 6.626 times 10 to the negative 34 joules, not per, joules times seconds. A joule is a unit of energy. Okay, so joules are just a unit of energy. So don't get tricked up by like, what is this? It's just a unit of energy. We can convert calories into joules. If you wanted your cereal box, it could be in the unit of joules instead of calories, very easily. Okay, but, okay, and then it's H times frequency again. Okay, and then we'll try some problems. Any questions on these for now? Okay, let's try a problem together of just how to use these equations. Before I go to that too, though, I know we have a lot of notes and not as excited these days. So everyone really quick, take a quick stretch break. Everyone stand up. 30 seconds. Tell your table what were the 5 things you're grateful for that you wrote down.
I wrote daylight saving. Oh yeah, daylight saving. I need to work right now. I've been doing daylight saving.
Second, right now. I'll be back, guys. I'll use the second one.
I have a backpack in my locker that's down there that is not my head. So I I'm gonna back up starting at the little patch of Sour Patch Kids.
Okay, grab a drink of water if you have some and have a seat. If you don't have water,
I got all of them. So for like 4 days. Did you know that Sour Patch Kids in pink and pink belly was orange and green?
well, let's work through these together just to kind of show you how they work. I wrote in purple there, those are what are on our formula sheet, so I just wrote them there so we could have them handy. Just once again, because, you know. And keep in mind, if you haven't noticed, once again, your formula sheet even defines variables. So you don't have to memorize that that funny shape is wavelength and that funny shape is frequency. It's on the formula sheet as well. Most of the time, if you just use them enough, you kind of just default memorize them. But they're always going to be there for you, especially at the end of the year. It's nice when we have to put everything together. Okay? So, question, let's go to the information given, then we'll answer question A. So it says, the diagram represents the photoelectric effect for a metal. When the metal surface is exposed to light with increasing frequency and energy of photons, electron first begins to be ejected from the metal when the energy of the photon is 3.3 times 10 to the negative 19 joules. Question A says, what is the frequency, so this is what I'm trying to find, of light? The light. I don't know why I put light there twice. Okay? So the goal here is frequency. So I have frequency in two equations, because it's our V symbol. The frequency of the light. So knowing which equation is based on what's given. So what was given in the initial problem? Energy. So this is the equation that's going to get me there. Because I have E and I want V. Okay? So if I take this and I rearrange it, what do I get? Good. So energy over H equals frequency. So I just took this equation and rearranged it for frequency, because that's what I'm trying to find. Alright, so whatever you're trying to find, get a loan. Okay? Now, as long as units match up, we can just plug in what's given. So 3.3 times 10 to the negative 19 joules is my energy, over H, which is just a constant, and it's in joules, so that's good too, because we want that to cancel. So 6.626 times 10 to the negative 34 joules times seconds. And then your calculator does the heavy lifting after that. I highly recommend if you have a graphing calculator, you know how to use the exponent shortcut that I showed you guys at the beginning of the year. It's really helpful with this, because you have times 10. If you don't use that, keep in mind that you have to put this whole thing in parentheses, otherwise order of operations won't work. Okay? The math isn't super hard, but the numbers are a little crazy, so sometimes the biggest mistakes I see made on these problems is just typing it into your calculator. So if you have your calculator, pull it out right now. I want everyone to try typing it in, and if you get the same answer as I do, you can have a smiley face.
I heard someone say that it was a favorite. It's not posted.
So you type the number in first, so type 3.3. And then yours now you only have to type this. Does that make sense?
Still not enough.
Alright, practice typing it in, compare with your table, see if you get the same answer. Negative 34. Yeah, it's our H value.
Oh, you put the minus instead of Hey, I did do it right.
Okay, that's what we got.
Alright, if you get that. Hold that one question, maybe ask it loud. Anyone not get the right numerical answer? This is what you should have gotten. So this is what I got, but then for sig figs, technically it's 5.0.
But do you count because of the 3.3?
So since this one only has 2 digits, yep, my answer only gets 2 digits.
But would you not just leave it at 4.9?
No, because of rounding. When you drop sig figs, you do check for rounding stuff. Questions? Anyone not need help with how they type it in? Okay, Lily asked a great question. We're gonna have her ask it again, because we all should be thinking it. Close your mouths here really quick. So ask it again, Lily.
What's the units for frequency?
So she said, what is the unit going to be? So if I come over here, the joules cancel away.
Seconds.
It's seconds, but it's not just seconds, because where's the seconds located? Yeah, so it's two ways to write it. You can write it as an inverse second, which is saying like per second. So the other way you could write it as like this, because you're saying the frequency is that many cycles per second. But that's what an inverse second means, is per second. So, questions on that? Yeah, first which one's more common to students? This one. Yeah. This one seems to make more sense to students, but this is like what you'd see on any problem. Good question. Okay, let's get to part B. So part B now, it says, based on the data table, what would the color of our light be? Okay, so we have a bunch of colors, but they give it to us in nanometers, which is wavelength. So we've got to convert to wavelength to compare it to my chart. Okay, so wavelength is our little, that symbol. So how did I get this one by itself? Good. So wavelength is C over V. C is a constant, 2.998 times 10 to the 8 meter per second. V is frequency, which we found in part A. So 5.0 times 10 to the 14. So once again, these problems can look a little intimidating because they have big numbers and lots of units. But when it comes down to it, it's just like division every time. It's just what you're moving over. Okay, so if I plug that into my calculator, I don't remember what I got. I guess I'll type it again. Oh no, it's right here still. How convenient. I got 6.0 times 10 to the negative 7 when I round it for suffix.
Oh, okay.
Good, so the unit on this is going to be a meter, because the seconds
Inverse
cancel each other out. But in order to pick the color, I do have to do one conversion step. What do I have to convert it to? Nanometers. Now, this relationship isn't on your formula sheet, so one you'll need to get very familiar with for when you need it. It is that there is 10 to the 9 nanometers in every 1 meter. So nanometers are very, very, very small in a sense. There's a, wait, what's 10 to the 9? A billion?
Sure.
Yeah, a billion nanometers in every 1 meter. So if I took a meter stick and cut it up into a billion pieces, that's how long a nanometer is. Okay, so they're teeny, teeny, tiny. So in the end, I get an answer of 600 nanometers, which tells me my color will be orange.
So much work just to find out a colors.
I know, someone last period was like, can I just look at it?
Yeah, I just like blue. Actually, no, I like 400.
Yes, close your eyes and use math.
Questions on using either of these equations? So homework 3.12 will have you practice using these equations a few times. Okay? All right, any questions there? One more thing to do? All right, last topic here, everybody. And then we'll be done.
All this work to figure out the 6
Okay, so this is where it now kind of connects back to our unit, because this deals back with solutions. I know the first ones kind of just feel like they kind of feel like random side topics. But this last topic, 3.13, is all about specifically UV spectroscopy and how it can be used to identify a molarity. So we have a third equation for today, also on our formula sheet. Okay, which is known as the Beer-Lambert law based on the people who derived it. Okay? This relationship is all about a solution and its relationship to concentration and how much it absorbs. Okay? So there's a lot of variables in this equation, but when it comes down to it, really only two are what we're going to focus on. So A, capital A is the absorption. What the absorption refers to is it refers to how much light a solution takes in. Back to our flashlight analogy, right? If this was a solution of something, copper sulfate, if I shine a light through it, to our eyes, it will probably appear all the light goes through. But at the molecular level, if it's a highly concentrated solution, those molecules in there can stop some of the light from passing through, and that refers to the absorption, versus if all of it just passes through. Okay? So the other one, so little, that funny little E looking symbol, this one is pretty much a constant every time because it's specific to the solution, and when you do this test, you stick with the same substance you're testing every time. B is also going to be a constant because you're going to use the same machine every time, and the only reason B would change is if you change machines, and like you're never going to just like change machines as you're doing an experiment because you want consistency. And then capital C is the concentration. So capital C represents the concentration, aka the molarity. So this is what connects back to what we learned last time. So using this method, we can determine the molarity of an unknown sample, right? Which is like pretty relevant data when it comes to certain things. When I was down at SGU, we had this thing called a water lab where companies would send in water samples for us to test for various things. And this was one of the tests we did. If we wanted to know what is the concentration of iron in this water, you can use this lab technique and tell them like, hey, there's like, this would be way too high, but like, oh, there's a 2 molar solution in your water of iron. Like, you should probably stop drinking it, right? Or whatever it is. So it's a very handy, and we'll do a lab with these devices sometime in the year. It was going to be Friday, but I might change it if none of us are going to be here Friday. So, okay, so this right here is a spectrophotometer for a UV vis. They're not very exciting on the outside. Maybe I should take one of these apart just to show you, but they're kind of pricey, so I don't know if I'm going to do that. But on the inside, there's a lot going on. Okay, so let's walk through the steps of how this works, and then hopefully make sense. Okay, so step number 1 is you put your sample that you're testing in the cuvette. Okay, the cuvette is the name for what goes in this. Where'd my cuvette go? Oh, they're cute little rectangular plastic or glass things. So this right here is a cuvette. Okay, you can see with the cuvette, they're designed where they have kind of like, they have a clear pathway, and then they have like a, I don't know what you call that, a not clear, fuzzy pathway, foggy, right? So they have like lines on one side, but then like that side's clear. The idea of that is there's a certain way you want to put it in the machine. You want to put it through so that light passes through it, not the graded way, okay? So we put our sample in our cuvette, okay? And then we place it inside your spectrophotometer, like so. Okay, they have little caps you can put on top of it. Doesn't really matter though, yes. So what's going on in the inside is that's where, in a sense, the flashlight is of lasers. So inside here is a light that can be controlled down to an individual wavelength, which is like a laser. And it's going to shine every possible color from 400 to 750 at this sample. Okay? So imagine a flashlight, but it's like changing what it does. What you get is this graph. So if you want to connect this graph to number 2, to know like this is what you get when you do number 2, is you get a graph that looks like this. That says, hey, at this wavelength, we got this absorbance. At this wavelength, we got this absorbance. What we're looking for is the maximum absorbance wavelength, because that's going to be what we want to test this sample at. So on this graph, what would be our maximum? Yeah, so right here, this is what we would call the max. Oh, I did that weird. Why did I draw that so funny? I don't know. That's supposed to be the wavelength, right? So this right here is our max wavelength, so about 525. So what that tells me is for this particular sample, I'm gonna run all my tests at just 525 now. Okay? All right, so now that I have my max wavelength, what we do is we create what is called a calibration curve. The calibration curve are using things we know their concentrations. Because if I want to find an unknown, I have to compare it to something that I already know. So what you make with a calibration curve is you make a series of known concentrations in incremental steps and test them to see what the absorption will be. Okay, so there's a graph like this. It's on the practice problem below, but connect that to number 3. Okay, so connect the line from number 3 down to this graph. This is your calibration curve. Okay, I in the lab, like we learned last time, created a 0.1 molar sample, a 0.2 molar sample, a 0.3 molar sample, and a 0.4 molar sample. I then place them each one at a time into my device. Okay, so imagine I put my 0.1 in here, I put it in there, I hit run on the computer, and the computer tells me it has an absorbance of this. I then take this one out, get a new one, put the 0.2 in it, put that in here, hit run, it tells me it has an absorbance of here. And the computer like generates the graph for me. Right? So that's how it's generated. And then after I run all my samples, I apply a line of best fit. Because it should always be a linear relationship. That's what's on that line right there. Okay, it should be linear. Now, obviously right here, I did something a little wrong with my samples because it's not perfectly linear. That's a human error problem because it should be perfectly linear. But I can still get my line of best fit. Okay? Questions on like what this graph is showing me and how it was generated? Now keep in mind all of these points were run at a wavelength of 525. So that's where that came into play. I only used that wavelength for my test. Now, here's the best part, is now comes the unknown. Is now that I have a curve generated, is I can determine an unknown concentration based off absorbance. So now I can take my random water sample, put it in here, put it in there, hit run. It will give me an absorbance value. I find where that absorbance falls on my calibration, and I can tell you its molarity. So we have to make this so then we can identify our unknown. We'll do that here in a practice problem in a second. Okay? Any questions for now on how this device works or the graphs that we get from it? Once again, we eventually will do a lab with one of these because I want you to get that hands-on experience, but for now, any questions? Okay, let's take a look at an example problem that looks really big, but hopefully you'll realize is not too bad. Okay, so in this problem, the whole first paragraph is just describing the process I just said, right? So they say a student is given a sample of copper sulfate that contains a solid impurity that is soluble and colorless. The student wants to determine how much copper sulfate is in the sample and decides to use a spectrophotometer. First, the student prepares a calibration graph by measuring the absorbances of copper sulfate solutions of known concentrations. So that's how we made the graph. The question said the student dissolves the entire impure sample in enough water to make 100 mils. Then the student measures the absorbance of the solution and measures that the absorbance is 0.30. Determine the concentration of copper sulfate in the solution. So I come to my graph, I go to 0.3, I come to my line, I bring it down, and I estimate, I'd say a concentration of 0.05 molarity. And there's my answer for that giant paragraph of a question.
Are those all the questions?
Not entirely, but that's like a very common question you'll see, is given an unknown, just use the graph predicted. Which, like, if you don't know what you're looking at, can be very difficult, but if you understand how to read it, hopefully it's easy. So, does that make sense? Any questions? Yeah.
Okay, wait, so you went to 0.3, and how'd you get that, like, other one to go down?
So you connect it to the linear line,
Oh, okay.
and then find where it would fall. No, good clarification, Palmer. Any other questions? So the other type of question they love to ask Jack with these is error analysis questions. So So let's go to this example one. So the other type of question is having to predict what went wrong when you didn't do the experiment yourself. Okay? So they tell us a student uses, once again, spectrophotometry to determine the concentration of a cobalt chloride in a sample solution. First, the student prepares a set of solutions of known concentration. So it's again, they're describing that process of creating your calibration. And then they use it to determine the absorbance of each of the standard solutions at wavelengths of 510. So look, that was the max wavelength they found it to be. Okay. Finally, the student determines the absorbance of the sample of an unknown concentration. The student made the standard curve above. Which of the following most likely caused the error in the point the student plotted at 0.05 molarity? Okay, so everybody circle that dot, that's not where it belongs, and that's what we're trying to identify, is what could have gone wrong here. Now, the AP test loves error analysis questions, not just in this unit, but almost in every unit that has labs. They love to have you try to make a guess of what went wrong. The first thing you always need to think about is you need to make sure that your error matches the direction of the data mistake. In our case, is our data too high or too low of what it should have been? Good, so that's the first thing to identify because you need to match the logic there. Because it could be totally different if it was too high. It's still a problem, but the matching of it is totally different. So next to your dot, write too low of a concentration. I did something, I was a student, that made my concentration lower than what it should have been. So we need to pick an error of A, B, C, or D that matches a too low of a concentration problem. Okay, so let's go through these and see what matches that. So A says there was distilled water in the cuvette when the student put the standard solution in it. So if there was water in here already, and then I added my solution, is that going to make my concentration higher, lower, or not change it? Lower. It's going to make it lower, right? Because if there's water in there, you're diluting it down, right? So this is going to make it too low, and it ends up, this is our answer. I should have rearranged it so it wasn't the first one we looked at. But we'll go through the other ones just to see why not. But it matches the fact our dot's too low, this would make it too low, and so that's a logical reason for the error. Unlike B, B says there were a few drops of a 0.1 molar in the cuvette. So what type of error would that cause? Too high, good, because this is a higher concentration, and so if there's a higher concentration in there, it's going to bring it up, right? So this is too high of a problem. Still a problem, right? But it's just not the right direction of the error that happened. That's what I mean by making sure it matches the direction of the problem. Okay? All right, this one says a student uses a cuvette with a longer path length than the cuvette used for the other standard solutions. So what this is referring to is with our equation of A equals ABC is what we call it. Okay? Is it saying that B was higher? If B was higher, what would happen to absorbance? It would have been too high, right? So this is another issue of if they did do that, it would have resulted in a higher error, not a lower error. So whenever you see one that's about like an equation, I just think about the math and think about, okay, well if this went up, then that would go up, okay? And then last one, the student did not run a blank between the 0.05 molar sample solution and the one before it. So this is something I didn't quite explain with the general procedure, but when you test it, when you test your various samples, you kind of do this like back and forth where I test a blank and run it to make sure that it kind of is like calibrating it as you go, so that makes sure that the light passes all the way through. Then you take the blank out, you run your sample. Then you put the blank in, run a blank, run the next sample. So you gotta go back and forth. So this would cause a problem, but you can't know if it's gonna be too high or too low, because it could go either way when you don't run a blank. Because it just could mess up the calibration of it. Lily?
How long does it take for it to run one?
It's pretty quick. Like, I don't know, 10 seconds. maybe. Yeah, they're pretty quick now. A lot faster than they used to be. When I was in college back in the old days, you know how like that one graph right here? Right? So like when you guys make this graph, you just put your sample in and you just push a button and it just makes nothing. I had to do this by hand. This is the dumbest thing ever. We had to set the machine to 400, hit run. Set the machine to 401, hit run. Set it to 402, hit run. So dumb. I hated that device. But now it just does it all for you, so it's so nice. So, any other questions about UV spectroscopy in general? So for homework-wise, you have some homework that deals with 3.13, and then the Quinky Classroom quiz will bring in some more of this like error analysis idea, having you kind of practice that. Okay? Okay, you have 8 minutes till the bell. In order to leave my classroom, when the bell rings, you have to pass off one homework question. You pick from either 312 or 313, any one, but you have to raise your hand and pass off one of them with me before you go, just to get in one practice before the bell rings, okay? You got 8 minutes, like you got plenty. Last period only had 4 minutes and they all passed on. But take your pick if you want to do 313 or 312. I gotta see work with your answer, just like if it was an FRQ.